Okay, so where are we now? Last week I covered the estimation of spatial models by means of maximum likelihood. And the reason I cover that first is because it gives us the foundation to look at some of the specification tests that we will cover this week, many of which are based on the maximum likelihood principle. And so then after covering the specification tests this week, then next week we move to the non-maximum likelihood setup based on methods of moments. So then between those two, we'll have covered the basis of estimation, and then the specification tests arguably is the most important thing in practical work, because that's where you first assess whether you even have to address spatial questions at all. So, and typically, in a specification search, which we'll talk about on Wednesday, you first assess, is there a problem? What kind of a problem is it? What kind of alternative model do I need? So what I'm going to do today, again, is a little bit of review for some of you, maybe not for others, is just kind of go over, we're all on the same page, what are the basic concepts behind specification testing. And specification testing, by the way, I should point out, is particular to the classical statistical perspective. You know, in a Bayesian analysis, it's different. It's not the same approach at all. So then we look at different types of tests, and I'll discuss Moran's I, which many of you already know from an exploratory approach as a measure of spatial autocorrelation, but in a regression context, it's a little bit different. And then we move into the classic maximum likelihood-based tests. And I'm aware that for some of you this is going to be a repeat, but I'd like to re-emphasize it so that you have a good intuition for what is actually going on in these tests, because they are basically the workhorse of our specification testing. And then, depending on the time, but I think there might be time, I'll start covering the specific tests for spatial effects. And today, the Lagrange multiplier test, and then next, on Wednesday, we'll look at some specialized versions of that. So the readings, as usual, this is in the Anselin Ray book. If you're really interested in the technical material of how these Lagrange multiplier tests work, which are going to be the workhorses, then I have this paper that's just kind of a review paper and looks at some special cases as well that we don't cover in the class. So what is specification testing and why do we bother? So as we've seen a couple of weeks ago, this regression analysis framework, the estimation and inference framework, is based on a set of assumptions. And if these assumptions don't hold, we're in trouble, right? We saw, for example, that if we ignore a spatially lag that is significant, then our resulting estimates will be biased and their standard errors will be off. So the question is, in practice, how do you know whether you're in trouble, right? And the key issue here, and this is sometimes not obvious, but all the assumptions of the model pertain to this mathematical model that we talk about, which has to do with a linear specification with an error term. But the error term we actually cannot observe. What we can observe is the difference between observed and predicted, which is the residual. So the critical aspect of specification testing is to establish a formal connection between something that we compute for residuals and something that is relevant for the unobservable error terms. So if there is no connection between the residuals and the error terms, we're in trouble, because we're basically looking at two completely different things. As it turns out, there is a direct linear connection between the two, and in the limit, in some contexts, they approach each other, so the residuals can be treated as if they were the error terms, even though they really aren't. So that gives us a way to operationalize some of these concepts. And so the critical thing will then be, how can we, on the basis of these residuals, construct strategies to figure out whether or not some of these fundamental assumptions hold, okay? And just to refresh our memories, what are these fundamental assumptions? First of all, it's a linear specification. So it's a classic linear model, has in matrix notation, a vector of the dependent observations on the dependent variable, then a linear function of explanatory variables and this error term. And in the classic model, the error term has a constant variance and is not correlated. So what we're really saying here is, first of all, this is the hardest one, that our specification is for all practical purposes correct. So we don't model some nonlinear phenomenon with a linear model, and we have all the relevant variables in the specification. Then the other ones, which are a little more subtle, is that the error terms are indeed uncorrelated. That's what we're going to be interested in the spatial context, but also have a constant variance. And as we've already seen, some of the spatial models, specifically the spatial autoregressive model, with weight structures that have unequal number of neighbors, will induce heteroscedasticity, even though, in essence, the error term has constant variance. So then the challenge for us will be to be able to tell true heteroscedasticity from this byproduct of a spatial process. And the final issue, something that we won't talk about much this week, but we will revisit next week, is that the explanatory variables in the models are what is called exogenous. And exogenous means that they are basically not determined by the same system as the dependent variable. And the way that is operationalized is by establishing that the explanatory variables are uncorrelated with the error terms, right? And so that is, if that is not the case, if they are correlated with the error terms, then we have simultaneity. And so then we have to deal with that. Now, in maximum likelihood, that's really kind of hard to do. You really, in order to do it in maximum likelihood, you need a full model of all the endogeneities and all the interrelationships, which, you know, is not really very realistic. And so the way out, as we'll see next week, is to use instrumental variables. And so next week we'll deal with, in a sense, a much richer set of models, in that they don't only allow spatial effects, but they also, in addition, allow endogeneity, which is much more realistic in practice. So what can go wrong? The error variance is not constant. That's called heteroscedasticity. The errors are spatially correlated. We're omitting true spatial interaction. The problem in practice is that obviously more than one of these misspecifications can be present. And the other problem in practice, which I've already alluded to, is that specification tests for one type also have power typically for other types. So you think you're testing for spatial autocorrelation, but that test statistic also has power against, say, heteroscedasticity or non-normality. And so then it's a challenge in practice to figure out which one it is, right? And we'll talk about that again. So the two major alternative hypotheses that we will be concerned with here are, on the one hand, the spatial lag model, and on the other hand, the spatial error model. And just to repeat, the true model would be the one with the lag term in it. The model that we are trying to establish that this is in fact a true model is the one without the spatial lag. So put yourself in a context, you do an analysis, you run a regression, standard ordinary least squares. How can you tell from the results of this ordinary least squares estimation that this is not the right model? That in fact you are omitting a spatially lag dependent variable. So that's a challenge. Just to make sure you get this mindset, It's all about constrained and unconstrained models. And I've mentioned this before. Constraints means some parameter is set to 0. So if you set rho to 0, there is no spatially lag-dependent variable. So the standard regression model is the constrained one. Rho is 0. The spatial lag model is unconstrained. Rho can take on any value that you estimate, right? So it's important to keep this straight, which is constrained and which is unconstrained. You would think that constraint is worse, but in a sense, it's not really worse. It's the one that you start with. So you typically start with a model that is simpler than the most complex model. As we'll see later, there's also another way to approach it, is to start with the most complex model and then impose constraints and test those constraints. We'll talk about that on Wednesday. So the other alternative is the autoregressive error model. It's basically the same structure. You have a spatially lagged term, which in this case pertains to the error term. And again, the constrained model is a standard regression specification, which you get by setting lambda to 0. So lambda to 0, this lag part drops. So unconstrained is the model with the spatial autoregressive error term. Constrained is your standard regression specification. So how do we approach this? So they're all the same. And I repeat this a lot because I know from experience that this is a source of confusion, which one is constrained and which one is unconstrained. So the spatial lag model, the null hypothesis, is that there is no spatial lag. So that is our point of departure, is the standard regression model. The alternative hypothesis is that we're missing something, so we should introduce the spatial lag. So the question then, in terms of specification testing, is how can we tell? And the only thing we have to tell are the residuals. So how can we somehow structure the residuals in some kind of test or diagnostic so that we can tell that we're missing something? That, in fact, the null hypothesis should be rejected. So the fact that rho is 0 should be rejected in favor of an alternative that's a spatial lag model or a spatial error model. So it's always the same thing. And there's basically two broad classes of tests. And they're really very different in spirit. And you could almost say that one is a misspecification test and the other one is a specification test. So when you don't have a specific alternative, basically the bottom line is you want to make sure is your specification correct. If there's anything wrong with it, you want to know. And then you reject to know, right? Those are the diffuse tests because there's not one specific alternative. For example, you could think of this as my null is there is no spatial autocorrelation. The alternative is there is spatial autocorrelation. But unspecified, is this autoregressive? Is this moving average? Is this lag? Is this error? Which kind? I don't really care, right? The other types of tests are very specific. So they work in a very specific model, and they're called focus tests. And they would be tests, for example, where you say, okay, the null in a spatial lag model is that rho is 0. The alternative is that rho is not 0. What do we call that? We call that a significance test on rho in our, daily vocabulary. That's nothing but that. That's a very focused test. There's a very specific alternative. So there's basically two classes of these tests. The focused ones are all based on a very highly parametric maximum likelihood framework. That's why I cover that first. The diffuse ones are not. The diffuse ones are basically different flavors of Moran's eye. So diffuse tests, you reject the null. The null is no spatial autocorrelation, but the alternative is something, right? Not specified. And the main test that we will see to deal with that is Moran's I. Then the focus tests, that's much more complicated in a sense. I mean, in the end, it's not, but the way you get there is much more complicated. Because you need a fully specified model, which means you have to make assumptions, which means some of these assumptions may not hold, which means you have specification tests or specification tests in some sense, right? So if you have to assume normality, for example, and then you build a specification test, then you have to make sure that the normality assumption actually holds before you can do your specification test. So it's kind of like one step removed. You know, Moran's I, you don't have to assume anything. You can compute it, and you reject a null. In these highly focused tests, you set up a model. That model is only valid if certain hypotheses are valid. And so certain assumptions are valid, I should say. And so you have to make sure that these assumptions are in fact valid. So they then require specification tests as well. And then you get in a mess. Because in classical statistics, the p-value of a test is only valid if that test is carried out in isolation. If you have one test carried out after another test, that's called pre-testing. So then the p-value of the second test depends on what you decide in the first step. So it's no longer the same as if you had done this test in isolation. Now in practice, people typically use what I call instantaneous amnesia, right? So you do a test for normality, you say, okay, this is fine, then you do your next test, and you forget that you did this test for normality, because if you didn't forget it, you would have to compute your p-values conditional on the decision that you made in the first step, which is a statistical decision. This is not a deterministic thing. There has probability associated with this, and you need to take that into account, because you could have been wrong in the first step. Right? That's what the p-value is all about. So this typically is very messy, and unless you are a theoretical person, people kind of don't like to talk about this too much. But it's there. And it's the same problem if you do multiple tests. You know, you may have heard this, if you test long enough, it's going to be significant. Right? It is the same thing. If you do multiple comparisons, multiple tests, then these p-values are really not right. They're not correct. And so you think, for example, that it's p of 0.01, but in reality, because you've already done 4 tests before that, it's more like 0.20. And so if you are strict adherent to this, you get in trouble. So what do people do in practice? They're not strict adherents to it. They just kind of do it anyway, right? Or they become Bayesians. In the Bayesian framework, you don't have this problem, because everything is about chains of probabilities, so it's all calculated in there. So this is something you have to keep in mind. This stuff looks very rigorous and is very rigorous, but it is also kind of, I wouldn't say flawed, but weakened by this practice of multiple comparisons and pre-testing and sequential testing, where your software doesn't do any correction, right? And you really, now how much does this matter? You know, if you have a significance of point with 5 zeros and then a 1, it's not going to matter, right? That's not the right p-value, but for all practical purposes, that p-value, the right one, will be less than 0.01. So, you know, you don't really have to worry about it. However, when you are near the boundary of your decision point and you do a lot of pre-testing or multiple comparisons, you have to be very wary, because basically what you're putting all your trust in is this sacred p-value is really not that reliable. Okay, just keep that in mind. So the tests that we will see based on the maximum likelihood principle are a wall test, which you may not know under that name, but you probably do know asymptotic t-test, and you definitely know t-test, likelihood ratio test, and a Lagrange multiplier test or Rao score test, which you also may be less familiar with, but we'll go over all that stuff. Okay, first, diffuse test, Moran's eye, and a little bit of algebra here, just to give you a flavor of how this stuff works and how it's all put together. So, first principle, as I mentioned, we work with the residuals. And so we plug the residuals into the standard expression for Moran's eye, which is probably the most used global spatial autocorrelation coefficient. And Moran's eye looks a lot like a Pearson-type product correlation coefficient. So the numerator is this cross product of the residuals and the spatial lags of the residuals. So U prime, U is a column vector, so U prime is a row vector. WU is the spatial lag of the residuals. That's a column vector. So the product of these two is the sum of the cross products. For each term, the residual and the spatial lag of that residual. So you multiply these together and you add them all up. And then you divide it by something. And what do you divide it by? This strange term S0, which is the sum of all the weights in the spatial weights matrix. Now, if we have a row standardized weights matrix, we already talked about this, what is the sum of all the weights? N. Because each row sums to 1, and there are n rows. So the sum of all the weights is n. So that's the sum of all these cross products divided basically by how many of them there are, because the weights matrix, if the elements are 0, there is no cross product. So only these cross products matter when there are actual neighbors. So that's the numerator. So you can think of this like a cross product statistic similar to a Pearson correlation coefficient between the residual and its spatial lag. It's not the same, right? I didn't say it was the same. It just kind of looks like it. And then the denominator is the variance. Is the sum of squared residuals divided by the number of observations. So that's an estimate of the variance. Now, if we have row standardized weights, then these two n's, the n in the numerator and the n in the denominator, cancel each other out, and we have an expression like U prime WU, which is the cross product of the residuals and their spatial lags, divided by U prime U, which is the sum of squares, right? And if those of you who've been through multiple iterations of econometrics might recognize this, well, if you were taught like I was, you would recognize this like a matrix expression for the Durbin-Watson statistic. In some textbooks, you might see the Durbin-Watson statistic as U prime AU divided by U prime U. And A is this matrix with 1 minus 1, 1 minus 1 for the differences of the statistics over time. Formally, it's exactly the same. You just have to deal with this W instead of the A matrix. And if you remember from econometrics textbooks, the Durbin-Watson has these bounds. There isn't an exact, result for the Durbin-Watson. And similarly, for Moran's eye, the inference is not straightforward. I mean, you can do exact inference for Durbin-Watson, but you have to make a lot of assumptions. In the same way, you can do that for Moran's eye, but you have to make a lot of assumptions. So typically, especially as the data sets get larger and you can use other ways to get these results, asymptotic approximations, that's the route we go in practice. And just to give you a flavor of how this works, so when you read the literature and you see these kinds of things, you see where it's coming from. So this is a classic textbook result in econometrics. This makes the connection between the residual U and the unobserved error term E. And these two are connected. So U is a, if you wish, a linear transformation of the true error terms. And M is a matrix, but M is a really weird matrix. So if you look at the, gibberish here, this is M. And M is what is called an idempotent matrix, which means if you multiply it by itself, if you take its transpose, doesn't matter. You always have the same thing. And you can try this. You can just multiply it as by itself, and you end up with the same thing that you started with. So this is a very peculiar matrix. It's also a matrix that, unfortunately, you cannot invert. Because think of what would happen if you could invert it. Remember, I always said you cannot observe the error terms. Right? If you could invert M, you could get the error terms from the residuals. The error terms would be M inverse times the residuals. But you can't invert M. M doesn't have full rank. M has rank n minus k. And n minus k is the degrees of freedom of your regression. So, as it's sometimes put in textbooks, this isn't really correct, but the regression eats up k degrees of freedom. And because these k degrees of freedom have been used, you cannot go back in a one-to-one way. So what you could do is say, get n minus k uncorrelated residuals from this, but not n. Right? So there is a connection between the two, but it's imperfect. But for our purposes, it's good enough, because given assumptions on this error term, like uncorrelated, constant variance, if we want normally distributed, we can figure out, because we know how to deal with transformations of random variables, we can figure out what are the properties of the residuals. We have the residuals, we want to say something about these error terms. This provides the connection. This allows us to go from properties for the error term E to properties of the residual. And just to give you an example of some of this, let's look down here. So this just kind of repeats what I just said. We're interested in the denominator. We're interested in the expected value of the sum of squares of the residuals. This is a perfect, there's nothing spatial about this. Perfectly general result. Now, how do you do this? And I do want you to kind of get a flavor of this, because this stuff is all over the place in the literature. And there's a couple of important, I wouldn't call them tricks, but steps here. The first one is that because, the first one is that we replace the residuals by m times E. And because m is idempotent, we only need one of them. So it's really m prime m, but m prime m is m, so that simplifies. The second thing that we use is that E prime m prime E, in terms of matrix operations, what's the end result of this? So one is a row vector, the other one is a column vector. So the end result is, use this trick. 1 times n, n times 1, the end result is 1 times 1. 1 times 1 is a scalar. It's a simple number. And here we do this kind of very useful, you can call it a trick, and you'll see this a lot in econometrics. Because it is a scalar, it is equal to its trace. Now, the trace of a matrix is the sum of the diagonal elements. So the sum of the diagonal elements of a single number is that number. So because this is a single number, we can equate it to its trace, and then we can use all the tricks we can do with traces, which means we can move them around. You can have this circular moving of matrices, and the trace is always the same. This is a very fundamental property. So we start by moving E prime to the end, and so that's trace M E E prime. And so in terms of expected values, M is non-stochastic. We don't have to worry about it. And the second part is what we assume, sigma squared I. So there's the sigma squared, and what's left is the trace of M, and we know that that trace is n minus k. So we know that the expected value of the sum of squared residuals is the true variance multiplied by the degrees of freedom. Right? So the variance, an estimate for the variance, is the sum of squared residuals divided by the degrees of freedom, and on average this will be correct. That's an unbiased estimate. Okay, now we move to the spatial arena. It gets a little funkier, right? So we have this, the sum of the products of the residuals with their spatial lags. U prime WU. First thing, we replace U by ME and U prime by E prime M prime. Okay, but here the M's don't multiply each other yet, so we have to wait a bit. So we put in the trace thing, and then we start moving things around. And at the end, we end up with two M's next to each other, which just become one M again. So we end up that the expected value of the numerator in Moran's I is sigma squared times the trace of the weights matrix with M. Right. And then we're in business. We can approximate these moments by these expressions. The variance, I will spare you that, but it's the same approach. It's just a little more complicated. And we end up with this thing. So what do we do in practice? We do an approximation. We approximate the distribution of the statistic by a standard normal distribution. This is an approximation. This is not really the distribution of Moran's I. In fact, the distribution of Moran's I is very tricky because there's the distribution of a ratio of two quadratic forms. And if you go to your econometrics textbooks, that's not that easy to figure out. You can approximate it, and that's what happens here, but this is not exact. This is an approximation. Large samples, it's fine. Small samples, it's not. But this day and age, we don't have small samples anymore. So then what do? You take the Moran's I that you compute for your data, you take its theoretical expected value, that's that thing up there, you take its theoretical variance and take the square root, and you standardize it and look it up in a standard normal table. That's the approach. Now, as we'll see later, you can generalize this approach to other kind of residuals. So, for example, the residuals in a two-stage least squares regression. These are not OLS residuals. You don't have this kind of simple ME connection between the error terms and the residuals, but there is still a connection between the error terms and the residuals, albeit asymptotic. Another example is residuals in a discrete dependent model. So if you run a probit estimation where your dependent variable is 0, 1, there is a notion of a generalized residual, which you can then plug into Moran's I and do a test for spatial or a misspecification test based on the Moran's I logic. So these are all extensions. The one thing I do want to stress, and that's why it's in yellow, don't ever do a permutation approach on the Moran's I based on residuals in a regression. And the reason for that is that the permutation approach, the null is spatial randomness. So in an exploratory sense, you have any variable, you compute the Moran's I, and then you reshuffle the observations on the map multiple times, and you recompute it each time. That null is spatial randomness. However, the null in our case is spatial randomness, But for the error terms, the residuals, because they are, the way to put this is they eat up these degrees of freedom, they're already a little bit correlated. So you want to separate that type of correlation from the correlation that could be spatial correlation. So you don't want to say, oh, these residuals are spatially correlated, when in fact they're not. They're just correlated because they are residuals, right? And that's why there's a difference between inference in the exploratory context and inference as a regression diagnostic, where the Moran's eye actually has more complicated moments than in the exploratory setup. If you remember, the mean of Moran's eye in general is -1 over n minus 1. It's not the trace of mw divided by n minus k, right? That's a different thing. So keep that in mind. I know it's very tempting, and unfortunately I've seen it only too many times, and even in some software manuals. Don't do this. So this is what it looks like if you run GeoDa. If we have time, I'm going to run a little bit of a demo later, or else I'll do it on Wednesday. But, you know, in the result on the top is kind of the default. And why is that? It's because of this. You see these monsters? These are traces of big n by n matrices. So the default is not to do this, because as we'll see later, well, my preferred approach is to use the Lagrange multiplier statistics and not Moran's eye, and I'll elaborate on that later on. So that's why the default setting in GeoDa is not to compute this. If you insist, we will compute these big traces of these big matrices, and then you actually get the inference. Okay. So what's the deal with Moran's eye? So if you do not reject a null, then you're in great shape. And why is that? Because Moran's eye is really a fantastic misspecification test. It picks up all kinds of things. It has power against a whole range of possible alternatives. Unfortunately, not just spatial autocorrelation, and definitely not spatial error autocorrelation. This is often misinterpreted. Oftentimes, forget about heteroscedasticity and all these other things, but even in a spatial context, rejecting the null hypothesis in Moran's eye does not mean the alternative is error autocorrelation. It means that there is spatial autocorrelation of some form. What form is not clear, because the statistic has power against such a range of alternatives that it could be an error alternative, it could be a lag alternative, it could be a combination of that with some other misspecification. So if you reject the null in Moran's eye, you're not out of the woods yet. You basically know you have a problem. You do not know much about what this problem might be. On the other hand, if you do not reject a null, you're in great shape. That means that none of these possible alternatives that could have been picked up by the statistic were picked up by the statistic, and so you're pretty much home free. So that's how I look at Moran's eye. Now, in some context, Moran's eye is the only way to go, but then, luckily, you can actually show, it's not that easy, but it can be shown that there is some form of equivalence between Moran's eye and some of these other tests that we'll see, the more classic maximum likelihood-based tests. Okay, so, and you may know this already, but I'd like to go over it. So basically, there are three ways of thinking about specification tests in a maximum likelihood framework. And it's always comparing constrained and unconstrained. Okay. So what's the rationale? What's the bottom line? How do you approach this? Well, if you impose a constraint and you can't tell the difference between the constrained model and the unconstrained model, then the constraint is a good constraint. Right? Let's say, okay, you have a model and you set the coefficient to 0. And you can't tell the difference between the model with the coefficient set to 0 and the model with the coefficient not set to 0. That means that they're basically the same, right? And if they're basically the same, that means the constraint is a valid constraint. So how can you tell whether they're basically the same, or rather, how can you tell that they're not basically the same? Right? There's three ways of thinking about this. One way is to look at the estimate itself. Right? So you estimate the model and you get 10. So then the question is, how different is 10 from 0? Right? And you can't tell unless you know what the standard errors are. Right? Okay. The other way of saying, okay, here's my model with the constraint, my model without the constraint. How do they fit the data? And if the fit is different enough, right, then we reject the constraint. And the last one is a little less intuitive, has to do with the slope of the likelihood function. But let me show my picture. This is my picture. And this is not my picture. This is out of a, I mean, this is my picture, but the idea comes out of a classic textbook, right? This is actually using the Columbus data, and this is the actual likelihood function in the Columbus data. And you see it goes up and then it goes down. We saw this last week, right? So the maximum likelihood estimate is here, and to that estimate corresponds a value of the likelihood function, and to that value also corresponds a slope of the likelihood function. Namely, that's how we find the optimum. What is the optimum? It's the first partial derivative of the likelihood function, which is the slope of the likelihood function equal to 0. Slope equal to 0 is a horizontal. So here we go with our three principles. First principle is comparing our estimate to 0. So we have this difference. We can figure that out. The question is, how do we know if this difference is large enough? And for that, we need the variance. And if you've done this forever, this is a t-test. A t-test compares the difference of your estimate with the null hypothesis, in this case that's 0, and divides it by the standard error of the estimates. Right? So if this estimate, let's say it's 0.454 or something like that, if the standard error is 0.01, then you'll be pretty secure that 0.54 is actually different from 0, given its precision. But if it's 0.54 with a standard error of 2, you can't say that anymore. So you combine the estimate with its precision to be able to say whether it's actually different from 0. Right? And that's, you know this is a t-test, you've done this forever. The second one is a little bit trickier. So we have the likelihood function for our maximum likelihood estimate. And then we put in a constraint. So this is unconstrained. We put in a constraint. We set it to 0. And for 0, we can also compute what the likelihood is. And so now we're interested in the difference between these two likelihoods. You may know this as a likelihood ratio test. And how can we tell that this difference is actually significant? We need to have the precision of the likelihood. Now, the likelihood is something you compute from the sample, so it also has a standard error and a variance and a distribution. So this is a little trickier, but basically given the difference between these two likelihoods and the precision associated with that, we can again figure out whether this difference is large enough to reject the null being the constrained model. And then the Lagrange multiplier test is the same principle, but now it's even more abstract and esoteric, if you wish, but applied to the slope of the likelihood function. So at the maximum, the slope is 0, it's horizontal. At the constraint, the slope is whatever it is, but not 0. And this slope, since it is the partial derivative of the likelihood function, also has a distribution and a standard error. And so we'll again apply the same principle. It will be even more complicated operationally, that given this slope and given its standard error, how can we tell that this is different enough from 0? And that's the third principle. And these three principles are kind of the classic three testing principles, and we'll see how they apply in the spatial case. So the first one, the t-test, which you know as a t-test, is called the Waltz test, and that uses the value of the estimate, right? The likelihood ratio test is, as I said, likelihood is not really fit, but it's a measure of the objective function, but it's kind of a proxy for fit. And then Lagrange multiplier is the slope. The great thing is that these are in the limit all the same. In small samples, you have an inequality. And the inequality, or I should say a possible inequality. The Waltz test is always the largest value. The Lagrange multiplier or score test is always the smallest value. So you can have a situation right on the edge where the Waltz test, that's your t-test, rejects the null, and the Lagrange multiplier does not. And this happens, you know, occasionally. With larger and larger data sets, it happens less and less because you approximate the asymptotic properties. But this is something to keep in mind. Also, this inequality only holds in perfect circumstances. So if you have other things going wrong, such as heteroskedasticity, which actually in practice is often the rule rather than the exception, then this may not hold. And I have plenty of examples where this does not hold. So just to recap, the Waltz test is a t-test. So just to think about it, what does this require? It requires you to actually estimate a spatial model. Right? So you estimate the spatial lag model like we did last week, maximum likelihood estimate. We have its asymptotic standard error, and then we just divide the estimate by its asymptotic standard error, and that is, you know, asymptotically in the limit follows a standard normal distribution, or the classic case, the thing that is called the Waltz test is a square. And the square of a standard normal is a chi-square with 1 degree of freedom. So that's, you all know how to do this. The second one, so for example, in lag estimation, maximum likelihood in GeoDa, you have the z value. That's your standard normal thing. The square of it is a chi-square variant. And so just keep this in mind. We'll compare them as we go through them. So here, that would be highly significant. I think the significant value for chi-square with 1 degree of freedom is like 3.8 or something like that. So this is way, way larger. The likelihood ratio test. So the first, the t-test, we estimate the spatial model. For the likelihood ratio test, we actually have to estimate two models, the constrained and the unconstrained. The unconstrained will always have a larger likelihood, quote unquote, a better fit, than the constrained one. At best, they are the same. If the constraint is exactly correct, then there's no difference between the two. But if the unconstrained model will always have a better likelihood than the constrained model. If that's not the case, something's really wrong in your calculation, okay? So then if we have this, then we have the classic likelihood ratio, but if you take the logs, the log likelihoods, then the ratio is a difference. So typically this is expressed as such, twice the difference between the unconstrained and the constrained log likelihoods is chi-square with 1 degree of freedom. But you need two models. So you need to estimate the null model, the constrained model, that's the likelihood. Remember I showed this last week, how you could have that in there. Here's the lag model, that's the unconstrained log likelihood. And then we take the difference between the two times 2, and that's 44.6. And that is the value of the likelihood ratio test. Again, way significant, right? Then finally, the Lagrange multiplier test, that's the one with the slope. The handy thing about that, and that's why in the 80s and the 90s, Lagrange multiplier tests were all the rage, is that you don't have to estimate the alternative model. In other words, you never have to get into spatial econometrics at all. You just use the results of the constrained model. Constrained model being standard least squares regression. So you use the residuals of a standard least squares regression, and even though the actual derivation is quite complex and is based on the likelihood of the alternative model, you actually never have to estimate it. And this is even more attractive when your alternative model is very complicated, like a spatial probit model or a spatial count model or those kinds of things. So that's why these statistics are so popular and widely used. The problem is that their derivation is kind of a pain. So the expression is the score transpose, the inverse of the information matrix, and then the score again, and that is chi-square. Now, we saw last week the score is all these partial derivatives. We saw that they aren't very simple in the spatial models, and the second derivative is even more complicated in the spatial model. So basically what you have to do to get these test statistics is figure out all these partial derivatives, figure out their expected values, and then, that's the easy part, setting the spatial parameter to 0. And then things simplify greatly, as we'll see in a few minutes. Okay, so in a nutshell, the three approaches are traditional. You estimate a spatial model, you do an asymptotic t-test. If you also estimate the constrained model, which is the standard regression model, then you can do a likelihood ratio test. Requires two models. And then if you want to be lazy and you don't want to bother with the spatial model, you can use the Lagrange multiplier test based on the least squares residuals. Now, of these three tests, the one with the most power tends to be the likelihood ratio test. And you can kind of get an intuition for this because it uses more information. So the t-test uses information for one model. The Lagrange multiplier test uses information for one model. The likelihood ratio test uses information from two models. Right? So that's something you will see. So now we'll go a little bit technical, and I just want to give you again a sense for how this works. If you are a little rusty with matrix algebra, just believe me, you know. So the null and the alternative, this is the error model. One issue with the Lagrange multiplier tests is that they can tell some alternatives apart, but some they cannot tell apart. And the alternatives that they cannot tell apart are called locally equivalent alternatives. And in a nutshell, what this means for us is that we cannot tell the difference between autoregressive and moving average errors. We will be able to tell the difference between an error alternative and a lag alternative. But for the error alternative, we don't really know whether it's autoregressive or moving average. So in practice, that's something to think about. Okay, so how do we go about this? We partition the parameters between the one that we care about, in this case lambda, and the other ones. Then we figure out the score, the partial derivative, and we set lambda to 0. Then we figure out the information matrix, and we set lambda to 0. And because it's partitioned, that's the only parts we have to worry about are the parts that pertain to lambda. So this simplifies things in the error model because it's block diagonal. So just to refresh your memory from last week, this was our score. You see the monster traces and the inverses and all this big thing. So this is really complicated, but we plugging lambda 0. So what happens in the first one, this whole inverse thing goes away because it's the trace, you know, of the identity matrix times W. So that's the trace of W. And lucky for us, the way we define W is that there's no self-neighbors, so the diagonals are all 0. So the trace is 0, goes away. So the only thing that's left is the second part. So you see, these score tests or these Lagrange multiplier tests, they look kind of formidable because you do have to work with the log likelihood of the full model, the alternative model. But after you simplify them, it really simplifies a lot. And in fact, in standard econometrics, a lot of the Lagrange multiplier tests can be set up as a simple additional regression. So you take the residuals, square residuals or something, and you run them through another regression. In space, you can't do that. Okay, information matrix, again, just to have fun, lots of inverses and lots of complicated things. So we set lambda to 0 in the first term, so that is identity matrix, so that's trace of WW. And the second one is the trace of W prime W. So again, it starts off being very complicated. It ends up being very simple. And so then we just apply the formula, if you wish, and this is our Lagrange multiplier test. Now, if you paid attention, this looks an awful lot like a Moran xi. The Moran xi was standard normal. This is this is chi-squared. So you have to think if Moran xi squared would be chi-squared. How do these compare? So again, just a little bit of algebra, and you see there is a very close connection between the two. They're basically rescaled versions of each other. So the Moran xi and the Lagrange multiplier tests are not identical, but very similar. And as I mentioned earlier, you can show that the properties of Moran xi inherit from the properties of the Lagrange multiplier test. And some of the more recent results are actually more encouraging in that you can get this, remember I said this highly parametric, a lot of assumptions, normality, all that stuff. Well, you don't need that anymore. With modern asymptotics, you can have alternative central limit theorems that do not start with normality. They start with other things like symmetry and stuff like that, but much fewer assumptions so that you can apply this in contexts that are non-normal. And the properties, to a large extent, remain the same. Okay, the lag test, same idea, much more complicated. If you remember, the expressions for the, especially for the second partial derivatives, were much more complicated because the variance in the lag model was not block diagonal like it is in the error model. So that's something just for amusement. You see these expressions. basically the lag model looks very similar to the error model, except the cross product is the residuals and the spatial lag of the dependent variable, not the spatial lag of the residuals. And then the denominator term is this complex expression that has our traces here, but then also this other thing. And if you look at it very carefully, you see M is in there. That's our same M we had before. And basically, this is the residual squares, the residual sum of squares of the spatially lagged predicted variables regressed on the X original regressors. So this is all, looks very complicated, but it's very easy to compute. So that's then an LM test. And so basically, these are the kinds of diagnostics that one gets from a standard regression output, and I'll show you in a few minutes how that works in GeoDa and GeoDa space. So these are the ones that we deal with in what I covered today. The first one, Moran's I, the Lagrange multiplier test for the lag, and the Lagrange multiplier test for the error. And then on Wednesday, we'll see what these other ones mean, these robust ones, and we'll also see how you put it all together in a specification search. Okay? So, any questions at this point? It's all pretty straightforward. You know, once you get it, it's between unconstrained and constrained. How can you tell the difference? There are three ways to go about it: the value of the statistic, the fit of the model, and then this kind of weird one, the slope of the likelihood function. But as it turns out, the last one is the most practical one, because you don't have to estimate a spatial model. And in the old days, you know, before GeoDa and before SpaceStat, you really didn't want to estimate the spatial model because you didn't know how to do it, right? There was no software to do it. So let me, let's see. So I'm going to bring up first GeoDa. And this is all, you know, pretty straightforward. I'll load the US county data, and I have to load a weights matrix. And I'll take the Queen contiguity matrix. So at this point, we can do the regression diagnostics. So this is the regression dialog. We've seen this before. And then you have the different variables. And I'm just going to set up a, let's take our homicides. This time let's do 60. So we have the homicides, we have the resource deprivation, we have a population score, unemployment rate, divorce rate, and I forgot what this one was. That's kind of the basic model. You set up the weights file, very important. Now GeoDa always uses row standardized weights. So you don't have to think about it. It does it by default. So then last week we saw the spatial lag and spatial error. Now we're just going to focus on the classic regression model, and particularly on what is down here. So this is the standard regression output that we've seen before. Then these are the classic diagnostics, the multicollinearity condition number, the Jarque-Bera test. So this is a monster, right? This is a chi-square with 2 degrees of freedom. You know, what is it? 34,000. So this is way non-normal, right? And in the old days, we would say, oh, we're in trouble. We can't use our score tests. But as it turns out, we don't have to worry about that, because in lieu of assuming normality, we get normality from the large sample. So the Lagrange multiplier statistics properties kick in because of the large samples without having to assume normality. We can get away with much fewer assumptions. So this is not this is not that easy to blow up, I don't think. So what we see here is very strong rejection of the null by means of Moran's I, and next week we'll see a whole bunch of combinations of the types of results that you can run into. I concocted a whole bunch of examples where I basically could show you any possible combination. And so sometimes you find a very strong rejection of the null by means of Moran's I, but then the Lagrange multiplier tests don't do anything. And almost always, if that's the case, we have very strong non-normality or very strong heteroscedasticity. So that's an illustration. Those instances would be an illustration of where the Moran's I statistic has very strong power against these other alternatives. So then we see that this basically has very strong indication both with the Lagrange multiplier lag statistic and then the error statistic. And then just to continue our example, I did this to some extent last week, but not totally, because I skipped it. So if we run the lag model, it's here now. You see this thing down here. So this is a little awkward, I have to admit it. And we struggled with ways to give this information, because this is not a diagnostic. This is basically an alternative to your asymptotic t-test. So remember, in the previous step, so we have all three tests here for the lag model. We have the LM lag statistic here, which is on the constrained model based on the slope. And then here we have the unconstrained model. So we have the, if you wish, the square of this will be the wall test. And then the likelihood ratio test is twice the difference between the likelihood of the unconstrained model, which is here, and the constrained model. No, this is the unconstrained model and the constrained model, which is here. So that's this entry. So in a way, what this does in the background under the hood, it gets the likelihood from the least squares regression and then takes twice the difference with this one. So to get this result, you actually have to run two models, right? And it does under the hood, right? So this is not, I mean, people who start using GeoDa often get confused and think this is a likelihood ratio test on residual autocorrelation in the lag model. It is not. Okay, you can formulate a score test, a Lagrange multiplier test for residual autocorrelation in the lag model, but I purposely didn't put it in here because it, again, involves all these big matrices, and so it's basically impractical to compute for very large data sets. And we had this in SpaceStat. I had this in SpaceStat, but I decided not to put it in here because it's just basically too unwieldy computationally. So that's what this likelihood ratio statistic is. And then, of course, in the error model, it's the exact same thing. You know, you have the likelihood ratio test here, which is the difference, but twice the difference between the log likelihood of the unconstrained model up here and then the log likelihood of the constrained model down here. Okay. So, any questions? So you should all now be able to do this. The reason I go through this is because for your next deliverable, you actually have to do this. So let me close this off and quit GeoDa. And then we will do the same thing in GeoDa space. You see it's basically identical. So now we don't, we load the dbase file. this one here. And then in the model weights interface, we load the GAL file. And then we make our model. We had done homicide rates 60. We plop it in the Y. And then we plop the other ones, RD 60, PS 60. So this is our model specification. Standard, OLS, run. And this looks exactly like what we had in GeoDa, and unlike GeoDa, we can blow up these things a bit. So, I mean, if you checked, it's exactly the same result. The only difference is that by default, GeoDa space does not give you Moran's eye. And you can fix this. If you go here in this little wheel, you can set various options. And let me try to remember, I think it's here. Yeah. So diagnostics, OLS diagnostics, the white test, by default, it's not computed. If you want it, you can check this box. Moran's eye, by default, is not computed. You check this box, you save it, we run this again, and you see now we have Moran's eye computed with the value of the statistic. Okay, that's it. So now you should be able to run your initial regressions and do an initial specification test for spatial effects. You still don't know what to do next. That we'll talk about on Wednesday. So on Wednesday, I'll elaborate on what these robust tests are. I'll talk about the tests when you have two-stage least squares residuals, which is actually very easy because it's the same thing. And then talk about the specification testing and go over the different combinations. And it's really, I mean, even though I have a flow chart and the specification search may seem fairly mechanical, it really shouldn't be mechanical. You really have to think about this, because especially with larger data sets, it doesn't take much to find evidence to reject a null. You know, that's something to keep in mind. So these tests are very sensitive. So is there a little bit of evidence that does not match spatial randomness, it's going to reject a null. And sometimes that is because there is a spatial effect, but sometimes there is another much more serious thing to worry about, and it has to do with your model specification. So before you do anything, look at the general fit of your model. I mean, I can't tell you how many times people came to me with problems with their specification tests, and they had an R-square of 0.02. 0.02, not 20%, 2%. So if you have 2%, you know, you have other problems, right? So deal with those first. Okay, but if you have a decent model, then usually the specification tests work fairly well.